Okay, so we got this roller coaster, okay? And it's starting on the top of the first hill, moving at 0.200 meters per second. Okay, and it is 85 meters above the ground. Does it have kinetic energy? Does it have potential energy? It has both. Okay? The other point we're asked about is it goes down the first hill and up a crest to the crest of the second hill, 64 meters above the ground. So this is not obviously drawn to scale. That would be the final height, 64 meters. They want to know how fast is the roller coaster going here. Okay? Now, ignore the effect of frictional forces. So that means there's no work being done here, right? Okay, if there's no friction, then there's no work being done against friction, and our energy is conserved. That's why we can write that the initial energy equals the final energy, which I can then expand to say kinetic energy initial plus potential energy initial equals potential energy final plus kinetic energy final. Okay? Now, what I'm looking for is part of which one of those terms? Which one of those terms would have final speed in it?
EKF.
EKF, yeah. So I need to isolate EKF right now. What do I have to do with EPF? Subtract it over to the other side. All right, so I've got EK initial plus EP initial minus EP final equals EK final. All right, now I can expand again. Okay, everybody okay with those formulas?
The question asks for the kinetic energy instead of
Oh, right, I get ahead of myself because I always just go straight to the speed part. We'll get the kinetic energy, yeah. Okay, so now, right now, it's set up to solve what I want, right? The kinetic energy final. I'm all right with that? Okay, so can I just plug in numbers here? Yes. In this case, if I'm solving for the kinetic energy, do I have to include the mass? Yes. If I'm solving for energy, mass is part of that. Remember that energy, joules, are a kilogram meters squared per second squared. If I'm solving for a height or a speed, those happen regardless of the mass. Okay? Any massive part would have the same speed at that point because there's no friction, and only gravity is causing it to accelerate. So if I'm solving for an h or I'm solving for a v, I don't need the mass. But if I'm solving for energy, I do need the mass for that. Mass is part of energy. All right, so I would just plug in my numbers here. Okay, so that'll be, what was it, 840? 0.5 times 840 times 0.2 squared plus 840 times 9.81 times 85 minus 840 times 9.81 times 64. Okay, so there's our final kinetic energy. If I wanted to find the speed, then I would just divide that by half of m and square root it. And I would have the speed of the roller coaster at that point. Okay, everybody all right with that? That seem a little familiar from Science 10? I hope so. Okay. Did I lose anybody anywhere? Don't be afraid to say so if I did. Okay. I want you to try the pole vaulter question. Then I've got a video to show you about pole vault. Okay. So in pole, actually let's watch the video first, then it makes more sense. You have to see pole vault. In pole vault, what you're trying to do is obviously go over this bar using a pole. The purpose of the pole is to help you to convert your kinetic energy into potential energy. Get you higher up so you can clear the bar. Okay, you gotta follow me here. Okay, so you're gonna run with this bar, or with this pole, you're gonna run as fast as you can, and then as you get close to the bar, you plant the pole into a little pit. Okay, and once you do that, your kinetic energy starts to bend the pole. Okay, putting what kind of energy into the pole? Elastic potential energy. Okay, starts to bend the pole, and then the pole will do work on you, okay, by throwing you up in the air, exerting a force on you through a distance, converting that elastic potential energy into kinetic, then into gravitational potential, and then you put it in water. Okay? Now, sometimes you have to see it kind of in order to... All right, so this question's simplifying things just a little bit. We're just saying we're going to convert all of the kinetic energy of the run into gravitational potential energy. Okay? So it's like he's just going to go straight up, which you don't want to do in pole vault. You do need to have a little bit of forward velocity because there's no pads back on the runway. Also seen that one happen. Okay? So you want to make sure you have a little bit. But we're going to assume there's no forward. Okay? So this pole vaulter has a mass of 56 kilograms. We are looking for their maximum height if, when they are on their approach, they are moving at 8 meters per second, and their center of mass, so right about here, is 0.850 meters above the ground. We do have to consider that their mass is not on the ground, it's here. Okay, so they do have a little bit of initial what? Gravitational potential energy, right? Because their center of mass isn't on the ground. All right, so I want you to calculate what the maximum height would be. We already did B, we talked about that already. So I want you to see if you can calculate what height they could expect to reach, okay, given those numbers. So initially, they have both potential and kinetic energy. Would you agree? Okay. When they're going over the bar, we're assuming them to only have potential. Okay? We're not told about any friction or any other non-conserved forces. If we're not told about them, they don't exist, and we can assume energy is conserved. Okay? So we're going to say initial potential energy plus initial kinetic energy equals, in this case, the final potential. They have no kinetic energy at their maximum height. Okay, so I'm looking for the maximum height. I don't need to isolate anything yet. So I'm going to have m times g times h initial plus 1/2 mv initial squared equals m times g times h final. In this one, does the mass of the pole vaulter matter? It doesn't. Mass is in every term, okay? And mass isn't part of height, so I don't need it, okay? Any mass would reach the same height given the same conditions, okay? So, because I like to not have to do extra work, I'm going to get rid of the mass. You don't have to. You can put 56 in every time there's an m, but all the power to you if you want to do that, okay? So I'm going to get hf by itself, so I'm going to divide both sides by g, and then I'm just going to plug in my numbers. 9.81 times 0.85, okay, plus 1/2 times 8 squared, okay, divided by 9.81. Okay, so they're going to reach a height of 4.11 meters. Okay. If this was a high school athlete, that's a pretty respectable pole. Okay. I coached high school track and field for 20 years. I don't think I ever saw anybody go over 4 meters. Okay, that would be a pretty respectable pole vault. Okay. In high school, pole vault is high jump with a stick. Yeah. Okay. Now, we described the energy changes. Obviously, it starts out as it's kinetic. They're building up speed, and then they bend the pole to build up elastic potential energy. Then the pole does work, pushing them up, okay, giving them some kinetic. Then the kinetic turns into potential, and then as they fall, the potential turns back into kinetic, and they mercifully land on that big giant mat. Okay? All right, how are we feeling about this? Is feeling familiar now? Now, tomorrow, we are going to be doing a lab, and it's going to incorporate inclined planes, conservation of energy, and friction all into one lab. I know that makes it sound really complex, but it's really not. Okay, you're going to run a cart from the top of a ramp to the bottom of a ramp, and we're going to compare the energy at the top to the energy at the bottom. Okay, are they going to be the same or different? We're doing this in the real world, so yeah, they're going to be different, right? The car's going to make noise as it goes down the ramp. Okay, it's not going to have as much energy at the bottom because of friction. Okay, so what you'll be asked to do, when you start thinking ahead of this, is you're gonna be asked to figure out how, or figure out the coefficient of friction between the cart and the ramp, based on the change in energy between the top and the bottom. Okay, what's the only force doing work in that situation? Friction. Okay, so this lab is really going to like incorporate work energy theorem, friction, inclined planes, energy, all of that all into one thing. Okay. Okay. Okay, I want you to try that one. See how we do with that one. Ask this if I was, making up, let's say, an exam question. Okay, something like this. Okay, part A is the easy part. You just did a question like this. Okay, so part A, just figure out how fast it's going when it gets to ground level. At ground level, there is a sand pit. Okay, when the bowling ball hits the sand pit slows it down as it craters the sand pit, okay, or plows down into the sand to a depth of 0.85 meters. I want you to tell me how much force was exerted by the sand in stopping the bowling ball. So this combines two concepts to do with energy. How many people are struggling with part B? Okay, cool. Well, we do. And how many people have done part B? I think this. So the first part is just a law of conservation of energy question. Okay, so we're just doing EI equals EF. We're calculating the speed. Okay, initially, it's gonna have both potential and kinetic. At the end, it's only gonna have kinetic. Okay, we just wanna find the final speed, so mghi plus 1/2 mvi squared equals 1/2 mvf squared. Okay, gonna cancel all the m's, divide by 1/2, and square root. Okay, so what we'll have there is 9.81 times 100 plus 0.5 times 4.5 squared divided by 1/2. Okay, so it should be going 44.5 meters per second when it gets to the ground. I'm okay with that number? Okay, now, the last part can be solved two ways because I messed it up. Okay, you could do this as a Newton's second law question and go, okay, I'll find the acceleration because I know the distance over which it was stopped, knowing Vf would be 0. Or I could do it in one step, okay? And I could say, work is a change in energy. Is the sand taking away all of the bowling ball's energy? Okay, so force times distance equals 1/2 mv final squared. It's going to take all that kinetic energy and make it 0. Okay, so all I have to do is divide both sides by d, and I've got the force of the sand acting upwards. So that's 0.5 times 15 times that number there squared divided by 0.85. It's a lot of force up. That would be the resistive force of the sand upwards. Okay? Very common for me to do that because here's what I'm testing with a question like that. Can you tell when I'm asking you a conservation of energy question versus a work energy theorem question? Mathematically, they look a lot alike. In a conservation of energy question, energy doesn't change. In a work energy theorem question, energy does. So part B, it does change. I take it from that huge number to 0. But while it's falling, its energy stays the same. Just converts from potential to kinetic. Are we going to follow the difference there? Okay, that's a pretty typical exam kind of question for next week. All right, tomorrow, be ready to do a lab. Okay? It's pretty straightforward.